Torque, from Latin, to twist. If I apply a torque to an object, that means I am applying a force that causes it to twist or rotate. What are the factors that affect torque? Here in our diagram, we see that we have our axis of rotation here at point O, and we're applying a force to produce a torque at point P. Certainly, if we increase F, we will increase the amount of torque. Increasing the force increases the torque. That seems obvious. But there's more at work than just that. Also playing an important role is how far away from the axis of rotation do we apply the force. So this distance r also affects the amount of torque produced. And lastly, the angle at which we apply the force makes a difference. We'll measure the angle with respect to the radial direction, so we'll call that angle phi. And we can see here, once we define that angle phi, we can resolve our force into radial and tangential components. We'll label them Fr for the radial component of the force and Ft for the tangential component of the force. It turns out that this component of the force produces no torque. Only the tangential component is responsible for producing torque. So therefore, the angle phi will determine how much of the force is in the tangential direction. Let's look at an example. When I apply a torque to the door, it rotates and opens. The force of my arm pulling on the door has two components to it. There is the perpendicular component and there is the radial component. So only the perpendicular component creates a torque. If I were to put all of my force in the radial direction, the door doesn't rotate because there has to be a component of the force that's perpendicular. Radial force produces no torque. Only the perpendicular component produces the torque. Here's the equation for torque, and as you can see, R, F, and phi are all factors in determining how much torque is produced. To remove lug nuts when changing a flat tire, you must produce torque. What if the lug nuts are really tight and you're having a hard time removing them? What can you do?
You're having a hard time getting your lug nuts off when you have a flat tire to change the tire? Then stay tuned, because I'm going to show you how to get stuck lug nuts off of your tire. Now, unfortunately, lots of mechanics, myself included, use air impact wrenches to put lug nuts on. So if you get a flat tire like this, it can often be hard using one of these factory lug nut removers to get it off. Of course, the first thing you have to realize is these things are small, and arms are pretty much useless on these. So use your foot and your leg muscles. They're a lot stronger than most people's arms. Make sure the vehicle's parked with the parking brake on. Put your leg on. Just like mad. There it goes. But let's say your mechanic used a giant impact wrench like this and you can't get it off even with your leg. Well, then you get a long piece of pipe like this and act like Archimedes. Because with a long enough lever, hey, you can even move the whole earth. Out it comes. A long pipe gives you so much leverage, even your arms will be able to push it off.
With forces, we could say that the net force is the sum of the individual forces, and we wrote it like this: sigma F equals F net. The same can be said for torques. The sum of all the individual torques is equal to the total torque, or the net torque. So here in this diagram, or in this picture, we see a couple on a seesaw, and we're going to use the right-hand rule to determine which torque is positive and which torque is negative. So we see the man's torque produces a clockwise rotation, so that's a negative torque. The woman's torque produces a counterclockwise rotation, which is positive torque. So when we add the torques together, the sum of the torques, T1 is positive from the woman and T2 is negative from the man. And we can write that F times R times the sine of phi, and we see both the man and the woman have the same R distance, and the same sine phi. So we can rewrite this as just F1 minus F2 quantity R sine phi for the net torque produced by the two of them. So for equal R and equal sine phi, we see that the net torque is determined by the greater weight. And you can see when the son comes and gets on the seesaw, he's able to increase the force on the right side, producing a net torque in the clockwise direction and causing the seesaw to rotate. This is a neat little piece of equipment that I have. It's just a spindle that can rotate, and I can place weight on each arm, and I can adjust how far the weight is on the arm. So I can adjust the R distance. And right now, it's the same weight at the same R, so the torque produced by this one is this way, the torque produced by this one is this way. They cancel each other out. The net torque is 0. And if I move one of them to a greater R, now the torque on this side will be greater than that torque, and it will cause it to rotate. Our equation for torque is F times R times the sine of phi. We know that the order of multiplication is not important, so we can look at this as F times R sine of phi, or we can look at it as R times F sine phi. So this R sine phi, we're going to call that R perpendicular, and F sine phi we're going to call F perpendicular. And if you look up in this diagram here, you can see that in this right triangle right here, this is the opposite side of the angle phi. So this is R sine phi over here. And in this right triangle down here, this red vector is the side opposite phi. So this is F sine phi here, or F perpendicular. So you can calculate your torque one of two ways. You can use the full value of F times R perpendicular, or you can use the full value of R times F perpendicular. Either way works, and depending on the situation, one may be easier than the other. And this R perpendicular, we give it a name. It is called the moment arm, or you could call it the lever arm distance. This is a door closer, and you attach it to a door, and it produces a torque to close the door, thus the name door closer. So here, let's see it in action. So there you see the door closer at the top of the door, and when I release the door, it produces a torque and closes the door. If I want to hold the door open, then I have to hold the door with a force that produces a torque in the opposite direction. And when I let go, now the only torque is provided by the door closer. When my hand was there, the net torque is 0. The torque produced by me is equal and opposite to the torque produced by the door closer, and the door does not rotate. It stays at rest. Here I've got my scale attached to the door, and you can see it's got readings in newtons, and the harder I pull on the scale, the greater the reading on the scale is. So what I'm going to do is I'm going to see how much force does it take to hold the door open. My reading is about 25 newtons to hold open the door. So I saw my reading was about 25 newtons to hold open the door. Right now the force of me pulling on the door is an F perpendicular. But if I were to move my force outward, now only a component of my force is perpendicular. And you can see I'm having to hold with about 30 newtons now. And if I increase to even more, I'm having to pull much harder, almost 50 newtons, to hold the door open. And if I let the force go down to the 30 that it was at before, you can see the door closes. If I move back to perpendicular and open the door, I'm back to my 25 newtons. And if I change the angle this way, Again, to hold the door open, I have to pull harder, 35 newtons. And if I let it go back to 25, the door closes. And if I move it to the very outside edge of the door, I see it only takes 20 newtons to hold the door open, because my R distance is greater, so I need a less F to produce the same torque.